Okay, so we're all in agreement about next week. Next week we will, we'll have that second exam. Know those 3 cycles. And by the way, when you do those types of problems, make sure you spend quite a bit of time figuring out the properties are correct, okay? It's pretty much the only thing you have to go wrong. Yeah. So, now this chapter, which is chapter 10, we still have 11 and 12 to do. We've got a reasonable amount of time between now and the final to do some good parts on those. So this is refrigeration and heat pump systems. Before I start on this, if you guys remember that for power cycles you have for right, power cycle, right? Typically gets Q here, and gets Q in from here, gets U out there, and then in the process it creates W cycle. Right? Okay, this is a power cycle where the W cycle is obviously equal to Q in minus Q out, and the efficiency based on this is equal to W cycle divided by Q in, or simply equal to this divided by Q in, or 1 minus Q out divided by Q in. Okay? So a power cycle is a cycle, obviously, that generates work. Now, that's what we spent most of our time on for chapter 8 and 9. Now we've got a refrigeration cycle, which I kind of mentioned something before. It's still cold, operates between 2 reservoirs. You've got cold and hot reservoir, and this is your refrigeration cycle. And the goal of a refrigeration cycle is to cool the space, right? So that means here you're bringing in here Q cold, let's say, but you are putting in some work, and then you reject this entire heat in here, which we call QH. Okay? Now, based on this equation, obviously this W, QH is equal to W plus QC, right? And now we don't talk about efficiency, but we talk about coefficient of performance, right? Which is again output divided by input. The output is QC, and the input is the output divided by the input. The input is simply W, or simply QH minus QC. Now, if this is a heat pump, again, what is the difference between a heat pump and a refrigerator? It's the same thing, right? It's just the goal. The goal, typically, we keep calling the goal of a heat pump is to heat up the system, right? But, so the coefficient of performance for the heat pump is typically called gamma, and it's equal to the output divided by the input. The output that is desired is going to be QH divided by the input, which is W, which is QH minus QC. Okay? So this chapter is essentially looking at this type of cycle, okay? So the idea is again, it's a refrigeration cycle. We use it to cool space or to heat up space, and then we use different substances, to achieve that. In most cases, we use refrigerants that are in as vapor, for example, liquid, or maybe just gas. Okay, so we're going to look at both of these situations. In other words, where you have some type of refrigerant which kind of changes between between liquid and gas. That means there is a dome, right? There is a phase change. Just like when we did for power, right? The first chapter that we did was chapter 8, in which we talked about the Rankine cycle, which is a vapor power cycle. And power cycles tend to convert heat to work. That's the main idea, converting heat to work, right? For vapor power cycles, we convert the heat that is coming from water that is pressurized, to which we add heat. That means it's in superheated region, right? And then we'll pass it through a turbine. We extract the heat, and then we go through the condenser, right? And then we pump it again, and then we repeat the cycle all over again. But we also looked at at power cycles in which the substance stays a gas all the time. Example, the combustion cycle. When it's idealized, right? Everything is happening within a piston cylinder, right? Going through those 4 strokes, and then we are converting again heat to work, right? Or the Brighton cycle, right? Or the diesel cycle. And here it's kind of the same thing, right? So we will first look at refrigeration systems. Why are we looking at them? Is because we use them in industry a lot, obviously, because who doesn't makes use of refrigeration on a daily basis, obviously, to preserve food and air conditioning. They play prominent roles in our lives. Heat pumps, on the other hand, use them all the time, to heat up spaces. So many other examples of commercial and industrial use of refrigerations, which I'm not going to get into, but air separation, to obtain liquid oxygen, liquid nitrogen, liquefactions, and so forth. But for us, at this introductory level, it's just really understand this cycle and what's happening through that cycle, or how do we create a cycle that would achieve that. So the objective is to describe some of the common types of refrigeration and heat pump systems presently in use. Now, as I indicated a moment ago, 3 principal ones are vapor compression. So we're going to do some vapor compression. There is another one which is called an absorption. That's an interesting one that we're going to be looking into. That's a cycle in which actually the refrigerant gets mixed with water, and not necessarily water, but which another substance. As it goes through the cycle, then the 2 substances get separated again, and we're going to look at why and how that is done. And then, of course, we will look at the case where the refrigerant remains a gas all the time. So we're going to learn about all those. Now, there are 7 sections in here. And so we'll start first with the easy one, vapor refrigeration systems. That's the case where the refrigerant could be in 2 phases, depending on the pressure and temperature. And then how do we analyze vapor compression refrigeration systems? And we look at a good example, and that's the example that I want you to know. In fact, it's an example that's kind of in line with the Rankine cycle, this and that, so you should be familiar with that. In section 3, we'll talk about refrigerant properties. What are the typical refrigerants that are being used today? And then we'll look at some modifications of this cycle, in which we have cascade and multi-stage vapor compression. You probably heard this term before. Anytime we look at a cycle, we look at how we increase the efficiency somehow, okay? So, and we just look at them, but we're not gonna be doing anything with them afterwards. Then we'll move on to another type of refrigeration, which is called the absorption refrigeration, okay? And then talk about heat pump systems, and then we'll finish with gas refrigeration systems. So 3 types of refrigerations that we'll be looking in this particular case. So, starting with the first one, what is the purpose of a refrigeration system? It's obviously to keep a cold region at a temperature below the temperature of its surroundings. Otherwise, why would you need it, right? The surrounding at a certain temperature, and you want something, you know, a place or space that you want to maintain at a temperature lower than that, then you need to have a refrigeration cycle, refrigeration system. So this is commonly achieved using the vapor refrigeration system that are subject to this section. Let's take a look at this figure here. As you remember here in the vapor power cycle, what we typically have is a boiler, right? And then we come in here, we come into a turbine, and then condenser, and then come back here, pump, and then come back in here, right? And remember, state 1 is this state. 1, 2, 3, and 4, right? And then this is where the Q in is occurring, right? And this is where the Q out is occurring. Okay, so this is the condenser, and this is WT. This is the work of the turbine. This is the work consumed by the pump, right? So that the net work is WT minus WP. So we want to create something like this for this guy, you know? Try to understand what's going on. So, in here, obviously, we typically have water vapor in this type of thing, right? We typically start in which region? Right? We always operate between 2 pressures, right? And then you usually come out, you either come out from here to there, right? 1, 2, 3, 4, and we call this A, right? Kind of schematically, you know, what is the, how the cycle looks like. In this particular case, we want to mimic this and try to figure out how is our thing going to look like. So first of all, we come in here and say, hey, we have now, as a working fluid here, we have water. Here we're gonna have a refrigerant, okay? So the common thing between those is that you are operating between 2 temperatures and 2 pressures. Same thing, right? That means on something like this, we have the low pressure, the low temperature, and the high pressure. So if you look at the 4 different components that you have, maybe an idea, since you want to keep this cold, right? The way you keep a place cold is you remove heat from it. And the part of the refrigeration system that removes heat is called the evaporator. Why? Because as the refrigerant is going through there and it's absorbing heat, it evaporates, right? So if my refrigerant is going through here, first of all, state 1 is always the compressor, entrance to the compressor. So you are compressing a refrigerant, you know, to increase its temperature and pressure, right? So you're going from 1 to 2. This is, by the way, an ideal, what we call the Carnot refrigeration cycle, right? Just like for this one, the Carnot looks like this. Carnot is this guy, right? Two isentropic and two constant temperatures, right? So in here, we're starting to compress the refrigerant. We increase its temperature, we increase its pressure. Okay, then what happens? Now we pass it through a condenser. What happens to the condenser? I mean, you go from vapor becomes liquid, that means you're removing heat. So one place you're adding heat, always think about this. You always have a spot where you're adding heat and one place where you are removing heat. Obviously, here we are extracting heat through the evaporator. Here we are rejecting heat to the warm region through the condenser, right? As you go here from 2 to 3, ideally you would end up as saturated liquid. Yes?
I forget, so, and I should know this because I used to work in HVAC. When you compress the refrigerant, that's when it wants to get rid of the heat, right? When it goes
Yes.
through, when it goes through.
When it
Like
goes through
in
the
this
condenser.
system, if we were
Yes.
air conditioning inside,
Yes.
when you send the refrigeration outside, it's
Yes.
compressed and then.
It's compressed and
it
the
wants
heat
to-
goes out.
Yeah,
Yes.
okay.
Yeah.
So like, I know these things are all theoretical,
Mhm.
but if I'm thinking about a house
Mhm.
or just a refrigeration, an HVAC system, what the heck would the turbine be?
Good question. It's coming up.
Okay.
It's coming up. We have a comment on that. You know, it's useless in this particular case for a good reason. So here we're trying to talk about it just to kind of do it as this, but you're not going to generate. The purpose of a turbine is obviously to generate work, right? If you're generating work through an expansion, right? Look at this, between 3 and 4, what is the state of my substance? Is it mostly vapor or mostly liquid? So when it's mostly liquid, it's really incompressible or stuff like that. So if anything, you're not gonna get diddly, nothing, right? So that's why people kind of get rid of this, because it's useless, and they just replace it with what they call an expansion valve. An expansion valve that just brings you from the high pressure to the low pressure without any losses whatsoever. Okay? So, but theoretically, in the beginning, since we don't know much about this, we're saying that we're coming in, now we are ending as saturated liquid, right? But still at high pressure, right? So if we go saturated liquid at high pressure, I come in here and throw it through the turbine, which is not a good idea to start with, right? You get a bunch of liquid that you're expanding through the turbine. And then you generate theoretically some little work, and then after that you're going from 3 to 4 isentropically. Now you end up with really low quality, right? And then you pass it through here at constant temperature through the evaporator. As it passes through, it sucks up some more heat, you know, from here.
When it's low pressure.
When it's low pressure, yes. So, it sucks up the heat at low pressure and then rejects the heat at high pressure. That's really how it is. Because at high pressure, that's where you get hot, right? And then you reject it back. So, when you look at this, this is an ideal Carnot vapor refrigeration cycle in which all processes are internally reversible, because we are assuming that there's no pressure loss as you're going through heat exchangers. There is no pressure loss, and we know for fluids there will be pressure loss in reality when you are flowing through any pipe of any kind, even if the flow is laminar. But we're assuming that no such thing exists. And because this is a TS diagram, the net area under the curve represents what? It represents obviously the net heat transfer or the net work, because the two are equal when you're talking about a cycle. And here we're not talking about efficiency, but we talk about coefficient of performance. We call it max because the Q's now become what? The Q's become T's, right? That's how you go from actual to the Carnot, okay? Now keep this in mind. So we have a compressor, condenser, turbine, and evaporators. A few more comments on this. it says the actual refrigeration cycles depart significantly from the Carnot cycle, you know, and the coefficient of performance would be much lower than that TC, because remember beta max, he said, is equal to TC over TH minus TC, because that curve that we have kind of looks like this. We are operating between two temperatures. And we're coming in here from state 1 to state 2 to state 3 to state 4. Okay, so this is our presumed Carnot cycle. It says one of the most significant departures is related to the heat transfer between the refrigerant and the two regions, in that they are not accomplished reversibly as presumed before. So again, we're assuming that everything here is occurring reversibly, but in reality, in order to have, so this temperature TH is the temperature of the hot reservoir. The temperature here, TC, is the temperature of the cold reservoir, right? Theoretically speaking, in order for heat transfer to occur here, let's say from the cold region to the, from the refrigerant to the cold region, so from the cold region to the refrigerant, the temperature TC prime of the refrigerant has to be lower than the temperature of the surrounding, right? Because now the surrounding, if there is the surrounding is at high temperature than the temperature of the refrigerant, then heat always goes from hot to cold. Okay, as we will see when you take heat transfer class, it's one of the key things for heat transfer. In fact, either one of the three modes that we will be studying next term, each one of them will depend upon temperature difference in one way or the other. Okay, so when we say reversibly for Carnot, you know, you gotta have something that is different. So if I have the surrounding that is transferring heat to the refrigerant, that means that the temperature of the surrounding has to be higher than the temperature of the refrigerant. At the same time here at the hot end, if I want the refrigerant to lose heat to the outside, right? To transfer heat to the outside, that means that the temperature of the refrigerant has to be higher than that, so that you can have this heat transfer, or you can, so you can have the heat transfer from the refrigerant to, because this is the temperature of the refrigerant. Again, this is just a comment, okay? We're not gonna worry about it. This is just going like from what's happening with an ideal Carnot cycle to the real thing. Now, look at this equation just for a moment. If TC prime gets lower, what does it tend to do to this thing? If the numerator gets smaller, it tends to decrease, right? Now, if TH minus TC now becomes TH prime minus TC prime, which is larger. If I divide by some number that is bigger, then this thing becomes even smaller. So this is kind of just an illustration that in real life, you know, the efficiency is going to be much smaller than what you are seeing in here, okay? And this is what I meant to say. Maintaining the refrigerant temperatures in the heat exchangers at TC prime, T prime C and T prime H, rather than TC and TH, has the effect of reducing the coefficient of performance, okay? Another problem of interest in here is the following, okay? We're still now analyzing this Carnot cycle. Even when the temperature differences between the refrigerant and warm and cold region are taken into account, there are other features that make vapor refrigeration impractical. as a prototype. You know, the one that has the compressor, the condenser, the turbine, and then the evaporator. It's impractical. Why? First of all, in the compression process, as I go from 1 to 2, okay? It occurs with the refrigerant in, I'm under the dome, it's two-phase, okay? It occurs with the refrigerant as a two-phase liquid vapor mixture. And you are going into a compressor, right? It's a compressor, you want to have dry compression rather than, you know, having vapor in there, right? So this is commonly referred to as wet compression when you have the two-phase, which is normally avoided to prevent compressor damage, because now you're pressurizing some vapor, you know, refrigerant vapors that have masses, right? And then they could damage your compressor. In actual system, the compressor handles vapor only, so this is known as dry compression. So this is impractical. This is not good. I would rather start from where? Probably from here and go up. Number 2, another feature is when you come back here from 3 to 4. What's happening from 3 to 4? That's, remember when we came back through the turbine that you were asking about, okay? Impractical is the expansion process from saturated liquid to the low quality, saturated liquid to the low quality two-phase liquid vapor at state 4. This expansion produces a relatively small amount of work, because remember, work is the integral of PDV. When you are very close to the liquid, the specific volume, it's liquid, almost liquidy, you know, it doesn't change very much, okay? So the expansion produces a relatively small amount of work compared to the work input in the compression process, right? As opposed to when you are on the right-hand side. So people are going like, okay, at the compressor, I'm using work and I'm trying to get technically a little bit of turbine work, you know, to make up for that, but it's really not much. The work that you're inputting here is so dominant compared to the work that you would be getting through the turbine. So people are going, why do we even need to have one, right? If I have to consider the cost of maintenance and this and that, so forget about it. The work output achieved by the actual turbine would be smaller. And this is also when you consider the fact that turbines are not really very efficient, you know, all the time. So even that small theoretical amount of work would be even smaller when you consider that the efficiency is low. Accordingly, the work output of the turbine is sacrificed. So that means in refrigeration cycle, forget about the turbines, you know. So we have the evaporator, compressor, condenser, and then that turbine, we have to replace something with it because we still need to get from the high pressure to the low pressure. So we need a component that's going to allow us to do that. And it says substituting that by a throttling valve. That's what throttling valve does, you know, without any losses of energy, you know, just reduces that pressure for the expansion turbine with a consequent saving in initial and maintenance cost. Now, with that said, see that big, ugly looking cycle that we had before now looks like this. You got 4 components, just like the vapor power cycle. In the vapor power cycle, we were going kind of in a clockwise direction. In here, we're going in a counterclockwise direction. And state 1 is the entrance to the compressor. Always remember that, okay? So, do all these values make sense to you? Remember, for a compressor, where does this equation come from, you think? What is it a result of? Remember when we were doing the vapor power cycles? Like, for example, if I were to say here, what is WT divided by M equal to, just based on this? What would it be? H1 minus H2, yeah. H1 minus H2. Remember, it's all finding all those 4 H's, right? and which one is higher because we're neglecting, it's really the first law of thermodynamics for an open system, right? By neglecting the terms that do not make any change. So here, as I go, for example, where is the enthalpy higher? Is it at 2 or at 1? At 2, because you're compressing it, you're adding energy to the system. So the work then done on the compressor is equal to H2 minus H1, period. Condenser, same idea. Here you're removing heat, so H3 is going to be less than H2, right? And this difference is translated through the amount of heat that is lost. The only thing you need to remember for refrigeration cycle is that for the expansion valve, no need to do any work, any stuff. H3 is equal to H4. Remember, for refrigeration cycle, for vapor power cycle, I always tell you need to find 4 values of H for refrigeration rate. Why? Because 3 and 4 theoretically are the same. Okay? And when you come back to the evaporator, obviously here you're gaining, you're evaporating, you're gaining enthalpy. So H1 is going to be higher than H4, and that difference is due to the amount of heat that was added to the system. Okay? So all here you have all the equations that you need for this type of cycle, and the amount of work is this. What is the efficiency? Not efficiency, coefficient of performance, I should correct myself. It's, remember what the goal for this one is going to be Q in, right? And then the amount of work is WC. So Q in divided by WC, and therefore it's going to be H1 minus H4 divided by H2 minus H1.
Is the evaporator effectively a boiler?
It's a heat exchanger. It's not a boiler because it's not an active thing, right? So it passes through the medium, right?
Yeah.
And as it passes through the medium, it's just sucking up heat,
Okay.
right? So a boiler, obviously, is a different story. You gotta have some fossil fuels that
Okay.
you're burning before you do that. So, what else? Heat transfer from the refrigerant to the cooler surrounding here. And this one is the heat transfer from the refrigerated space into the vaporization of the refrigerant. And as obviously, in here, you're gonna get some, the amount of heat. And notice in here, by the way, state number 1, where did we move state number 1 to? Well, state 1 is the entrance to the compressor. See, in the Carnot, it started here, but for our cycle, it's going to start at saturated or superheated. Okay? Why? Because we want to have dry compression. We don't want to compress vapor. Okay, one unit that you need to be familiar with, Q in is the refrigeration capacity in kilowatts or BTUs per hour. Another unit is the ton of refrigeration that is used, I think, in the field or in the trade. It says that it's the ton of refrigeration represents 211 kilojoules per minute or 200 BTUs per minute. Okay, so it's just another unit. Okay? Sometimes you calculate things in kilojoules per minute, and to convert that to tons, you just divide by 200, and you should get the answer in tons. So then this is the TS diagram for an ideal vapor compression cycle. This is the cycle that you need to be familiar with, right? We're starting where? From entrance to the compressor at saturated vapor, right? And we are compressing how? Isentropically, constant S, and then to the higher pressure. That means state number 2 will always be in superheated. I mean, it's a no-brainer. You're moving up, you have the dome, right? And then after that, you have what is this process here? 2 to 3. It's at constant pressure. Yeah, because this is a pressure line, right? When you get to 3 3 has to be at saturated liquid, right? So when you get to station 3, finding what this value of H is no brainer. It's just the HF for that particular pressure, right? And then H4 is going to be equal to H3. But here, why do we have it slanted like this? You think? Because it's not an isentropic process. You know, when you're going through, you're going through an expansion throttling valve, right? Even though there is no heat transfer, but it is not it's not reversible, so it gets accompanied by a slight increase in entropy. That's why we kind of show it like this, okay? It says heat transfer 4 to 1, 3 to 4, throttling process from 3 to 4 to a 2-phase liquid vapor mixture, and then 4 to 1, heat transfer to the refrigerant as it flows at constant pressure again through the evaporator to complete the cycle. There is a note here at the end that says that all processes are reversible except for the throttling process. Now, let's take a look at this example here. Just need to just look at this one. This is the typical cycle that's going to be in that you need to be familiar with. It's refrigerant 134A is the working fluid. Some other ones would be different refrigerants. When it says in an ideal vapor compression cycle that communicates thermally with a cold region at 0 and a warm region at 26. So this is TH and this is TC. Clearly these are in degree C, which need to be converted to Kelvin. Saturated vapor enters the compressor at 0 degrees and saturated liquid leaves the condenser at 26. The mass flow rate is given at 0.08, and then you have about 4 questions. What is the compressor power? What is the refrigeration capacity? What is the, by the way, when we say refrigeration capacity, is really what is this Q that you are removing, you know, from the cold space, or QC. What is the coefficient of performance, you know, of a Carnot refrigeration cycle operating between warm and cold region, respectively, okay? Remember, anytime you're asked about Carnot, the only thing you need to do is change the Q's to T's, okay? So how do you do a problem like this? You always have to, it makes life a lot easier if you draw the physical mechanism and the TS diagram, okay? So annotated, okay? So this is the evaporator, this is the condenser. QC is 0 degrees, which is 273. It's 26, which is 299, right? And this is showing the ideal cycle, right? Starts at saturated vapor, isentropic, finishes here at saturated liquid, little increase in H, and you move on, okay? And as is the case for vapor power cycle, to do this one, you just need to find what the 4 H's are. Right, so once you find those, then it's a no-brainer. So if you wanna take a look quickly here at what is 134. First of all, state number 1 is what? But what is the how do you know state number 1? What is given about state number 1?
Temp.
The temperature is given, right? What else? Is that it? Well, the temperature and
State.
saturated
Vapor.
vapor.
It's
Okay.
on the
All right.
line.
Yeah. So it's pretty clear then what it is. Do you need to be given the pressure? if I were to ask you what is the pressure of that vapor at state one, what would it be?
2.92,
What table are you looking at?
110.
110?
I think so.
Get to the table here. So 134A is a 10, right?
Yeah.
So at a temperature of, what did we say, 0?
26.
So.
No, no,
6.8.
at state 1, the temperature is 0,
Oh,
isn't it?
0, yeah.
2.9.
2.9.
2.9, yeah, so that's what the pressure is, okay? So what is H for state number 1?
247.
247.23. Okay, that's pretty much it, okay? Now, before I move to the next section, what else should I read?
The S.
The S, because it's the isotropic process, right? And the value of S should be 0.919. Okay, you guys are rocking, good. Let's see. So, it's really what it is. See, 247.23 and 0.919 for state number 1. Now, state number 2 is well defined because we know the entropy. And what else do we know? Do we know the temperature or do we know the what else do we know about state
Entropy.
2? Okay, so at the pressure at state number 2, because we don't know the temperature of state number 2. We don't. We don't know that, I should say, we don't know the temperature at state number 2 because we are not within the dome, you know, to say we are there, right? In fact, look at this drawing right here. See when you draw it? 26 is right there, but now my temperature is going to be much higher than 26. But what I do know though is that this pressure is what? Is the pressure that is corresponding to it's the saturation pressure that corresponds to the 26, which is again looking at that temperature, and I hope the temperature is there.
6.853 bar.
26 is 6.853, yes. Okay, now you know that pressure, so that means now state 2 is well defined because we know its pressure and we know its temperature. Now, how am I going to find what is that? What is the H? I know that state number 2 now is in superheated, so I need to move on to the next table, right? Instead of being at A11, I think, right? I need to go to A12. And when you go to A12, what you are searching for is the state that has that pressure that you just got. And 6.85 for the entropy, right? So coming back in here, so the pressure at state number 2 is that 6.83 bar, as you guys recognized. So state 2 is fixed by P2, which is this pressure, and the fact that the specific entropy is the same as the previous case, okay? So, so when you look at that state, obviously P2 is 6.853 bar. Now, unfortunately, you have to do, well, you always have to interpolate when you are in that table, you know. So you got 2 point on page 836. 836, there is 6 bar, there is 7 bar, and then there is 8 bar. Okay, 6 and 7, right? Somewhere in there. And then state 2S is given by P2, and the fact that specific entropy for that is that, and obviously you get 246.7, 264. You know, from looking just at those values, they are about in the right range.
Can we just use the 265?
So, you know, 265. Well, as long as the value is pretty close to this, I think that's fine.
So we're supposed to use the S1.
S1 is, what is S1? 0.919. You see,
So how do we,
This way, just to then interpolate that way.
so we're supposed to find between a 919,
Because you don't have.
0.919 on this one here, that's pretty darn close for
it's not-
4.7, for 7 bars.
yeah.
0.919 is almost like a 265 degrees. I mean, you can interpolate back, it's probably gonna be 265.
Because isn't 919 below?
Yeah, it should be.
Because there isn't a number, the 919 isn't between,
919 is between 0.9197 and 0.9080,
isn't it?
right?
Oh, okay, yeah, sorry, I was looking at it the wrong way, okay.
See, so
Yeah.
it's a little bit less
Well.
than that, you know? And then for
Okay.
the 6 bar
Okay.
or for the 6 bar, you kind of look at that too. So
Okay.
you interpolate
Okay.
both there and then you do the
Yeah,
linear.
okay.
Double interpolation,
Oh.
I guess.
That's just me.
But it is what it is, you know, it's, so you get that state, but the nice thing about this is by the time you get to state, that's the only state that has work in it.
Everything else is on the bar.
Everything else is just the stuff, so, you know, it makes life easy for you, but here, that's probably the only point that you have to be really careful with is state number 2. Because state number 3, remember at 26 degrees, right? What is HF? Is it 26? I think that's 26. HF should be, what the heck is it? 8575, somewhere around there? Yeah, there you go, 8575. So H for state number 3 is you just read it directly for that particular temperature is just the HF. And then H4 you don't have to do anything because H4 is equal to H3. So H4 will also be equal to 8573. Now after that, it's just, you know, the equations are fairly clear. What you need to do, you just plug in, for example, what is the compressor work? And you go, oh, compressor is between 1 and 2, right? So it's W divided by M is, or W is equal to M dot times H2 minus H1, right? And M dot is given to you, H2 you got, H1 you got, so it's 1.4 kilowatts, all right? And then the rest of the stuff is also fairly straightforward. What is the refrigeration capacity? Refrigeration capacity, remember, you're removing heat through the evaporator between H1 and H4, right? H1 is higher than H4, so it's going to be M dot H1 minus H4, but you're told to express that in tons, right? That means you do here the conversion, right? 1 ton is 211 kilojoules per minute, and you get 3.67 tons. Done. Number 3, what is the maximum, what is the coefficient of performance? Remember, the actual coefficient of performance, which is what it is a function of what? You know, of the H's. In other words, Q in divided by WC, and we know what Q in is, H1 minus H4, so you find 9.24. And what is the Carnot one? The Carnot is only a function of the reservoir temperatures, and thank God this number is higher than this, otherwise it means we have screwed up somewhere, right? And that's it. That's all there is to it for vapor refrigeration cycles. I think it's easier than vapor power cycles, you know, because most of the values are pretty well defined. Saturated vapor, saturated liquid, and this one is the same thing as saturated liquid. The only one that you need to do is H2, in which you have to interpolate. Okay, moving on now to, and I'm just going to mention this in passing. For actual cycles, obviously, the heat transfers between the refrigerant and the cold and warm regions are not
reversible. If they are not reversible, that means they are not isentropic. And if they are not isentropic, that means there will always be some entropy production, okay? If there is some entropy production, that means that H2 technically is slightly higher than H2S, right? So the dashed line is drawn to show that the increase in specific entropy that would accompany an adiabatic irreversible process. This effect can be accounted for by using the isentropic compressor efficiency. Now, I did not really spend too much time on this, but I keep repeating that the only use for the compression efficiency is that it will allow you to find H2 based on H2S. In other words, it's going to be one extra calculation when you introduce this effect, into the analysis, right? So instead of going from 1 to 2S, which was done in the previous problem, when we go there, before we go to 3, we go back and actually find an actual H2 by using this equation, and then we move on. In fact, the book repeats that same problem as we did before, except that it says here that, what does it say? Well, this is a different story. This is not the efficiency. This is saying that, remember what we said before? In order for the heat transfer to occur, you're going to have a temperature here of the refrigerant that is higher, and that the temperature of the refrigerant that's going to be lower. If in reality it's not happening isentropically at constant, reversibly. So modify example to allow for the temperature difference between the refrigerant and the warm and cold regions. And remember what we said before, anytime you account for this, that means that the efficiency goes, or the coefficient of performance goes down. In the previous one, we calculated that as being 10 point something, right? In here, if my temperature is 0, right, and here you're told, assume that you are 10 degrees below here, and if here you are at 26, right, assume that the pressure is actually 9 bars instead of that 8 point something, right? And then you have to redo the same calculations as before, and then compare the results. So this problem is identical to the previous one that we have done. So in a sense that you're just using different states, obviously, to figure out what the values are going to be, because state number 1 clearly is where? Case number 1, instead of being at 0 degrees, is going to be at -10. That's the only thing that changes, right? It's still saturated vapor at this, right? So it means you read the value at -10, you read S at -10, it's like a broken record, really. So, but all I'm interested in is this. Look at the value of how much it dropped. See, it was like 10 point something before, right? Now, when those temperatures are different, when you take into account the fact that things are not really reversible, right? That means that the efficiency drops down to about 4.57. And this one is the one that I was wanting to look at, is repeating that same example now, but with an efficiency now. Now this problem involves what? Involves the fact that this temperature is -10, this is 30, but now we are not efficient in here either. In other words, we have, the compressor has a compressor efficiency that is not 100%. What do you expect that beta to do? Well, it's going to go further down. Anytime you introduce an irreversibility, you are paying the price at the coefficient of performance, okay? So again, without looking at the numbers here, you do this, and let's see. I just want to go to the final result. See where the coefficient of performance that was 4 point something before, because of that irreversibility of the compressor, it comes down to 3.86. So you can play around with so many inefficiencies and this and that. The analysis is obviously identical, but you are just the more irreversibility that you introduce, the less that coefficient of performance is going to be. Okay, moving on now to section number 3. And now that we have talked about the ideal refrigeration cycle, how to take care of that. Refrigerant properties, obviously up to 1990, the most common class of refrigerants used in vapor compression was the chlorine containing ones, the CFCs, the chlorofluorocarbons, right? The CFCs, like refrigerant one was one of these, refrigerant 12, right? The problem is this really chlorine stuff, atoms. Owing to the detrimental effect, once they figured out that chlorine actually affects the ozone, right? And then you probably remember in the 90s, people were going like, oh, take away that refrigerant and this and that, Freon and, it's all that kind of good stuff. Owing to the detrimental effect of chlorine on the ozone, then international agreements have been implemented to phase out the CFCs, okay? So instead of doing CFCs, they were using HFCs, hydrofluorocarbons. So classes of refrigerant containing various amounts of hydrogen, so that's what they were trying to do, is they wanted to replace the hydrogen in place of the chlorine atoms, right? So remove as much chlorine as possible, if totality of it. So they have been developed and they have less potential to deplete the ozone than do more fully chlorinated ones, such as R12, okay? And then now we have the HFCs, which contain no chlorine, okay? So again, what to retain from here is that chlorine was recognized to be bad, and then steps were taken to phase it out, and I don't think now we have anything that's got those. Now refrigerant 134A is the HFC. See here, we've got hydrogen here instead of chlorine, considered by many to be environmentally acceptable substitute for refrigerant 12. 134 has replaced R12 in many applications.
What makes a good refrigerant? Is it volatility or?
Well, it depends on the application, unfortunately, because it depends on how much really Q, because you could have a small refrigerant like on a lab scale, for example. You just need to keep something that is just a few degrees below the stuff.
Alright.
So you could use maybe just a regular gas to achieve that. But other than that, the fact that obviously at room temperatures those things are volatile, they usually you are trying to cool a space that is below what the conditions are at the atmosphere, right? So what you want to do is you want to have those at atmospheric pressure. If you look at the properties of the refrigerant when it's 1 atmosphere, they're just going to be a gas, so that they could do their job at least in the at the evaporated level. Refrigerant 22 it's another HCFC, and then there is the other ones, ammonia, propane, methane, and such gases as carbon monoxide are under investigation for use as refrigerants. Because again, the whole idea here is you are compressing something, right? And then you pass it through the stuff, you remove the heat from it, right? You bring it back, and then you pass it through another heat exchanger, essentially, to suck up the heat, to change its phase, and you move on, okay? So in the HVAC field, people tend to use the pH diagram, right? Because when you work in HVAC, you say, oh, you're operating between this pressure and that pressure, right? And you need the enthalpies, right? So you see a lot of these diagrams widely used in the refrigeration field, because clearly you have 2 pressures. Remember, the low pressure is the evaporator pressure, the high pressure is the condenser pressure, and these lines are drawn as this is most like the PV diagram, but kind of just it's a PS diagram. the pH diagram, sorry, in which you have the constant entropy lines. And remember the way we are starting from an evaporator pressure, you know, you're going isentropically to state number 2, and then condenser pressure, everything is constant. And why do they do this? Because really between 3 and 4, remember what we said, that the H's are the same. So you're really dropping down vertically, right? And then you move on. Maybe a better diagram is really how you go from, this is what engineers like to use, this is what people in the field like to use, you know, just like what.
I remember seeing those things everywhere. They're like a flat cardboard.
Flat
slide
cardboard,
ruler
and then
kind
they
of thing.
slide them back and forth,
Yeah.
yes, you know, so it's easy to read quick, you know, you don't have to, it's like they call them nomographs or something like this, I forgot how they do these sliding scales. So pH diagram shows the main features of a TS diagram to the left, okay? An engineer is more kind of figures this better, right? But somebody in the field just needs to read values directly from there. Property tables and pH diagrams for many refrigerants are given in handbooks dealing with refrigeration. But obviously, in our case, what we need to do is, just like we have tables here for various refrigerants, we know where to go to read those values. Now, in terms of selecting refrigerants, now, the temperature of the refrigerant in the evaporator and condenser, because eventually when it gets to here, you know, it's got a certain TC and it got a certain TH, are governed by the temperatures of the cold and warm region, you know? It's not just one size fits all, right? You know, maybe you're working in an environment that is really hot, right? So your TH here is going to be really hot, so your refrigerant temperature obviously is going to change accordingly if your surrounding fluid, right, or the temperature of the cold reservoir changes, the temperature of your thing changes and the temperature here changes. That's why it says the temperatures of refrigerants in the evaporator and condenser are governed by the temperatures of the cold and warm regions with which the system interacts. This in turn determines the operating pressures in the evaporator and condenser, because as you are going through the evaporator of the condenser, everything is happening at constant pressure, right? So if you know what that temperature in the outside is, it dictates what your temperatures of the refrigerants are, and it dictates what the saturated pressures are for both cases. Consequently, the selection of refrigerant is based partly on the suitability of this pressure-temperature relationship in the range of the particular application. So after you select that, you know what your TH, you know what your hot environment is, what is its temperature, you know what the cold environment is, and then you go like, okay, now my refrigerant has to be this and that, right? And this is the pressure, that's that pressure. Then depending on what refrigerant you're going to be using, then you have to do the calculations to figure out, am I really going to be able to extract that much amount of heat, you know, from the core space, etc. But the general rule of thumb is that they say it's generally desirable to avoid excessively low pressures in the evaporator and excessively high pressures in the condenser, right? Other considerations include chemical stability, toxicity, corrosiveness, and cost. This has something to do also with fluid flow. Anytime you design a heat exchanger, for example, people who design heat exchangers will have to face those types of issues, because you have to have a fluid that is flowing through a bunch of pipes, right? One idea that some people have is say, hey, you want the flow to be, remember we talked about this last week for those who are in fluids, flow in a pipe is of two kinds. It could be laminar, it could be turbulent, right? Laminar when it's kind of nice and orderly, turbulent when it is really chaotic. Turbulent flow extracts more heat, right? As opposed to laminar flow. But turbulent flow, on the other hand, will have a lot of shear stresses that develop within the fluid. That means you got high pressure losses, which goes against our basic assumption, okay? So that means avoid the high pressure stuff, right? But again, when you have it low, it's not really gonna do much, right? So you're gonna have somewhere in between. Of course, these are just two things, but other considerations include chemical stability, toxicity, corrosiveness, and cost. And there are a lot of people making their living just based on this. So we're not expected to know all that by looking at this. The type of compressor also affects the choice of the refrigerant, because compressors, as we'll see in fluids too, when we do turbo machines, you know, we'll study some of these. Centrifugal compressors are best suited for evaporated pressures of refrigerant with large specific volumes and low pressure. So it depends. Are you using, for example, large specific volume and low pressure, or the opposite, right? Low specific volume refrigerant, in which case you could use either centrifugal compressors or reciprocating ones. Again, these are just details that you really are not elaborated on in the okay, just as is the case for every time that we talked about the basic vapor compression system, right? There are some different ways of using them. For example, it says variation to the basic vapor compression system are used to improve the performance or for special applications. The book mentions just two of them, okay? The first one is when you use vapor compressions in series. In other words, and we've seen this in vapor power cycles too. Remember here what we have? We have a, let's say, a refrigerant. You are removing heat in here, right? And you are, dumping the whole thing in here. So what happens as you have one vapor power cycle in series with another one? Both of those obviously have to operate at different temperatures, you know? Maybe you're gonna have a low temperature one here, another high temperature one, right? So, and then what's going to link them is really what's happening here in between. So, schematically speaking, it's almost like when you have another refrigerant here, another cold, the main cold, right? And then here, technically, you're going to have a hot one, right? So you're gonna come in like this, and then this one will, again, you're gonna have kind of a heat exchanger that goes on, so that the main heat that you are removing is going to be from this side, and then the main heat that you're gonna be dumping is through there. Let me show you it's probably better seen when you do it in this particular fashion. It says the first is a combined arrangement in which refrigeration at relatively top temperature is achieved through a series vapor compression. And this is what I meant to say. You can probably see here there is one cycle, and then there is one cycle, right? Right at the QH, right? At the top in here, where for the low one, when you come in through the compressor, right? What typically happens in here, you're losing heat, right? As opposed to here in which you're absorbing heat. So you're losing heat, and this helps in vaporizing the one at the top. Does that make sense? You know, so it says combined cycle arrangement for refrigeration are called cascade, and sometimes you see these in like 2 or 3. You know, it's like cascade, 2 or 3 of them. In the intermediate heat exchanger, this is the intermediate heat exchanger. The energy rejected during condensation, which is right there, in the lower temperature cycle A, because lower temperature cycle will tend to reject heat here, is used to evaporate the refrigerant that is in the other cycle, which is the higher temperature cycle. Why do we call this the higher one? Because obviously this temperature has to be much higher than this temperature. So we call this the low temperature one, the low temperature cycle. This is the high temperature cycle. Now, when you look at this, you go like, if I look at this system here as a whole, the desired refrigeration effect, where is it occurring? It's obviously occurring right there, right? The Q in here. And heat rejection overall is happening where? In the high temperature condenser, right? Because this is just a heat exchanger, becomes like an internal component. Whatever is lost by one is gained by the other. So there is no net effect, if you will. However, when you look at the coefficient of performance, it's really the output, which is Q in, divided by the input. Now I'm inputting the net is the sum of the two, right? That means the work of the compressor at A plus the work of the compressor at B. Okay? So, and we've done this for the vapor power cycles when we use different fluids and so forth. In a double cascade system, the refrigerant would be selected for cycle A that has saturation pressure that allows refrigeration at a relatively low temperature. That's why we call it the low temperature one. And in B would have saturation that permits condensation at the required temperature without excessively high condenser pressure. Okay? So low temperature and high one. Number two, another improvement, if you will, not improvement, but well, kind of an improvement, if you will. Look at this now. Do you want to analyze, do you agree that this is a bit more complicated than the regular refrigeration cycle? At first sight, when you look at it, you go, what the heck is this, What does it mean, right? First of all, instead of having 4 states, how many do we have here?
Too many?
Too many. In fact, at least 9, or if you include the A, it's going to be 10 states, okay? And that's not fun, right? But what does it really mean? Because initially, what did we have? We had just the evaporator, the compressor. And from the compressor, we went directly to where? Just to the condenser, right? And then to the expansion valve and then to the evaporator. We had 4 components, right? And we got many more in here. Now, and the many more, so in here we're starting, let's say, from 1 to 2, right? As you go from 1 to 2, instead of, remember, this is called, anytime you use many turbines, we call that multi-stage expansion, right? If you use many compressors, it's multi-stage compression, right? This qualifies as a multi-stage, even though it's only 2 stages, right? So you are operating between the low pressure, high pressure. Anytime you have multi-stage, that means you have some intermediate pressure in between. In other words, you're not compressing directly to the higher pressure. So what's happening in here? First of all, you don't have the entire refrigerant that is flowing through here, right? It's only 1 minus X. We'll figure out why in just a second. So you're going from 1 to 2, okay? Then what happens between 2 and 3? You have what we call a direct contact heat exchanger. Direct contact heat exchanger, you know that heat exchangers typically exchange heat, that you're either gaining heat or losing heat. What do you think happens in here? Maybe before we go there, you go like, what the heck is coming through here? So let's take it one step further. After you come back from the condenser, right? What typically happens at the condenser between 4 and 5? You're going from, let's say, superheated to saturated liquid, right? And as you go from saturated liquid, then 5 to 6, what happens? You are expanding to that middle, to that intermediate pressure. Then what happens? You come into a flush chamber. What is the state of my refrigerant in the flush chamber, you think? At 6. some of it is liquid, some of it is vapor, because it's two-phase. A flash chamber is a chamber which allows you to actually separate the liquid on its own and the vapor on its own. So what you do here, you extract the liquid phase and let it go through here, because that's really what you want, right? And then the vapor one, which is kind of cold, right? What do? You pass it through this direct contact heat exchanger. So what happens to this darn thing that you compressed when it gets mixed with something that is cool? So you got a fraction, let's say you got 9/10 coming here at a high temperature, right? And then you mix it with 1/10 of lower, so that result, and of course it's happening at constant pressure, so you end up with what? You end up with that same pressure but lower temperature. Does that make sense? As you compress, what happens to the state of the thing? I mean, the temperature goes up, right? The pressure goes up. But when you mix it with something that is colder, then between 2 and 3, what happens to your temperature? It goes down, right? And then after to here, do we have the entire refrigerant at state number 3? The entire mass flow rate? Yeah, because you have X plus 1 minus X, which is 1, right? Now you come in, now you finish your compression isentropically between 3 and 4, okay? So what is the whole benefit of here? If we did not have the multiple stuff, we would have gone directly between 1 and A, right? By doing the multi-stage, I went to 2, boom, boom, right? What did I do? I removed this little area there, right? And that little area is, it's heat, right? Equivalent to some amount of work, right? So what happens is that intercooling is achieved in gas power system by heat transfer to the lower temperature surrounding. In a refrigeration system, the refrigerant temperature is below that of the surrounding for much of the cycle, so other means must be employed to accomplish intercooling and achieve the saving in the compressor output. See, I'm saving this amount of work, right? So if you're saving some work in the compressor, what happens to the coefficient of performance? It increases the coefficient of performance, right? Because remember, coefficient of performance is Q in divided by W of the compressor. So if you reduce the work of the compressor, you are increasing the efficiency. That's the only idea behind this, okay? Intercooling is accomplished in the cycle by direct contact heat exchanger, right here. In the flash chamber, which is right there, the liquid and vapor components are separated into 2 streams, okay? One stream is coming through here, the other stream is coming through there to accomplish the rest of it. Okay. It looks like we are making headways here. You guys want to take a little breather here before we? Yeah, let's do 5. Oh, yeah.
Sorry, I can have my
Let's see.
No, it's okay.
It's also my other one.
There I go. Okay, thanks. I think I may have it. There we go.
So there's a midterm next.
Next Monday, as I was telling you guys.
Diesel, auto, rate, and second.
That's it.
Look at the examples.
Look at the examples,
Kinda
not
good.
reading.
Okay.
Sort of kind of like this. So, you know how to do that.
What? Oh, I'm You've been looking at it?
No, I haven't,
I think if you search just for the, like, title of the class, like, whatever it is, Mech 313,
okay.
I think it might come up. You can search for my names.
Okay.
I think there is some relatively famous artist named Scott Robinson, so he might come up too.
You're not taking credit for that one?
I'm not nervous. Good. We were down there today for a little bit. Didn't see you there. Yeah, we'll be there tomorrow.
We finishing 10 today or
We'll be
no?
there a lot.
Hmm?
Are we gonna finish 10 today?
I doubt it. I think I'm gonna live a little bit. I don't wanna rush it. But we're gonna do 10-5, finish 10-5, talk about heat pumps. And that's probably, then we're just gonna have gas refrigeration ones, so we'll see how the time goes. It's almost done. This chapter's almost done. So if we finish it, then next week we'll just do the exam directly. Instead of lecturing.
Oh, okay.
Did you say, at least for chapter 10, like for the final, do we need to know that actual vapor compression refrigeration cycle?
Actual, what do you mean actual?
Well,
That is the ideal.
there's the ideal,
Yes.
and then there's the actual.
Yeah, the actual only has that, what is it called? You know, yeah, just the ideal,
Just the ideal?
yeah.
Okay. Because the actual one has a funny looking TS graph on it.
Yeah. Which is example
10.3.
10.3, yeah. Yeah, because that's a combination of that increase in temperature on both sides. So it's a little complication that is really unnecessary in my opinion. I mean, for purposes of the final.
Right. Okay.
Are you gonna teach FEA? They said you might.
Yeah, I think I may. Yeah, I think I will.
Who teaches engineering materials now that Bridge doesn't?
I was curious. So I'll have you for 3 classes.
Next term?
If
What
you
do you
teach
have?
FEA.
I think I will be
And heat
here.
transfer.
Heat transfer,
And,
FEA, and fluids too.
It's not the big one. There's another one that's.
Hey, it's gonna be a ride.
By the water.
Do you think if I were to miss the day,
Oh, you're not been yet?
During the first
Oh,
week,
oh,
would that
okay.
be the best?
He got himself stuck
To
in
miss
the
you mean?
pipe for like 3
Yeah, I'm
days.
thinking about going home for a wedding, so I can see my brother-in-law.
So you're gonna miss
He
the
has,
first
he
week.
has cancer, he might not make it through the year. So I just want to see him, because he's my brother-in-law.
Mhm, mhm.
And, I mean, he keeps going out, in and out of the hospital. He has stage 4 kidney cancer. So I'm wondering, my wife's like, we need to make a decision. So let me talk to my professor and thinks,
Yeah,
if he
well-
thinks missing a week is gonna be tough, then I won't do it.
So you're gonna be missing in the 3
She
classes,
goes there
right?
when her kids.
Well,
I may only
if-
miss 2.
Yeah, which is fine, as long as you are up to date with it, you know, when you come back or before you go.
That's what I was thinking, try to just do some of the homework.
Yeah,
here.
yeah. So you know, maybe before you go and I maybe give you the syllabus.
It'll be right after the first week.
Right.
We start on the 30th. It's that weekend, I believe.
Yeah.
So that Friday to or that
Yeah,
Thursday to
I
Tuesday.
think you'll be able to manage, you know, you're just gonna probably, you know, work a little.
It's like I always
catch
have
up.
to. That's okay. All right.
Yeah, that's doable.
That's the part, that's the easy part. The
Yeah.
next part is the money decision. Do I want to spend $5,000? Because when you take the family, it starts adding up. You know? If it's just me, that'd be
Yeah.
a problem. They want to see the boys. My boys haven't been home in 5 years.
Hey.
Now my 14-year-old, he's basically a grown man. Last time they saw him, he was a kid. He was a little bitty dude. You know, now he's a big old. So I'm like, yeah, I gotta take the kid. He's gonna. Oh.
You know, decisions.
I told my wife, I was like, look, I'd rather pay off that debt and see him one more time before he
Yeah.
dies, or let him see the boy.
That makes sense.
Who knows? He might last 10 years, right? Some people keep going.
All right.
You got it? So we have a test next week, I hear.
Yeah, so, remember you were not here, you know, auto, diesel, ranking, right, from chapter 8.
What chapter 9?
No, chapter 9.
Chapter
sorry.
9.
Chapter 9.
Yeah, I was looking over the notes. I'll do some of the examples.
Yeah.
I'm gonna do the homework.
Yeah, if you look at the examples in the book, the first ones, you know, and be familiar with how to do them. They shouldn't have any problem. All right, I think everyone is here.
This next one.
All right, guys, let's start. So we've talked about vapor refrigeration cycles, you know, and we know the ideal refrigeration cycle for vapor. Operating between 2 pressures, right? Starting from this state, you go that way, right? Come back to here, go to 4, and you come back like this. That's it. Okay. On a TS diagram. So in this particular case, obviously the vapor changes phase, you know, and that's really what's going on. But there is another kind of refrigeration. Remember we said we're going to talk about 3 of them, right? This is the second one. It's called absorption, you know, just like its name indicates, there is some absorption phenomenon that happens. So absorption refrigeration cycles have some feature in common with a vapor compression cycle considered previously, but they differ in 2 aspects. So it's almost like taking that refrigeration cycle that we talked about before, but with a modification. What is the difference? First, One is in the nature of the compression process, which happens between 1 and 2. Instead of compressing a vapor between the evaporator and the condenser, the refrigerant of an absorption system is absorbed by a secondary substance called an absorbent. So before you compress it, right, you do that, and the reason for it is the following. You're taking a refrigerant that is kind of in a vapor phase, if you will, that gets absorbed by the liquid, by a liquid, okay, which is called an absorbent. And the liquid solution is then now not compressed. You don't use a compressor anymore. Now you need to pump it, right? So it's really in the nature of the substance in here, because a compressor, when you compress a substance, is a lot of work that you need to be doing, because remember integral of PDV, even if you're going between the two extreme pressures, the low and the high, a gas will tend to have a higher V than a liquid. You probably all agree with that when you look at the tables and everything. So the liquid solution is then pumped to the higher pressure, and this is the idea. Because the average specific volume of the liquid solution is less than that of the vapor, then much less work is required. That's the whole idea behind vapor pressure, vapor under compression. We will look at the schematic in just a second. That's the first difference that's occurring right here. The other main difference is that some means must be in absorption system, because by the time you come in between 2 and 3, what's happening? Here you are going through the condenser, right? Now, you don't want to have a mixture of water and refrigerant at the same time going through a condenser, right? Because they don't have the same properties, you know? So the other main difference is that some means must be introduced in the absorption system to retrieve, to separate, if you will, the refrigerant that was mixed initially with water, with the absorbent. So some absorption to retrieve the refrigerant from the liquid solution before the refrigeration enters the condenser, and obviously this involves heat transfer from a relatively high temperature source. A schematic is the best way to understand this type of thing. Okay, look at this. What do you recognize in here? You recognize the evaporator that's associated with the original cycle, the expansion valve, the condenser. What used to be here before? Just the compressor, right? Now, instead of having the compressor, we are replacing it with this entire stuff. What the heck is that? Look at this. Coming from the evaporator, instead of going directly to a compressor, now we're going through this absorber, okay? So we got some, we're absorbing some stuff, right? With some absorber liquid. Let's say this is water, this is a refrigerant, they get mixed, right? And obviously you need to keep this kind of in a liquid form, so you need to kind of run some cooling water just to make sure that it is in liquid phase. Then what happens after you come out, after you mix it, right? This is the absorption part, right? You come in here at state number A, now what do? You pump it. You pump that. What's coming out of here? It's a mixture of the liquid and the refrigerant that is now at higher pressure, right? Now, before going into the condenser, because what you want to go to the condenser is the refrigerant, not the liquid, not the mixture, right? So what you do, you need to pass it through what we call a generator. What the heck is a generator? Well, in the generator, heat, so what you do here, you have that mixture that you expose to really high temperature. Which one do you think is going to evaporate first? Is the liquid or the refrigerant? The refrigerant. The refrigerant is going to evaporate, and as it leaves, right, it leaves the solution, right, and the evaporator goes through here, right, and the liquid kind of stays. We call this the strong solution. What does strong solution mean? It means you have water that is rich in refrigerant, right? When you evaporate, do you think you're gonna evaporate 100%? Yeah, you're gonna have some traces left, right? And in this case, you're gonna have what we call a weak solution, right? That comes out, and you come in here and, you know, you put it back into the mix stuff, and then the process repeats itself. So let's read what's going on in here. It seems like a lot of work for just improving this work that you are inputting into the compressor.
What's the practical application for this? It seems a lot.
It's the same application as the original one, except that theoretically it is an improvement that would reduce the amount of compressor work that you are inputting and therefore get a better efficiency. That's all. The end result is exactly the same.
So it would be applicable in somewhere where the cost of electricity was so expensive
Where
that
it's
buying this whole system.
Yeah, you have to do an analysis. You can't just look at something and say it is fine. You know, you got to factor in the maintenance work. Now you got the pump. You got
More components.
more components because there are some issues that we're going to be talking about in just a second. So it says, for example, in this case, ammonia is the refrigerant and water is the absorbent. Let's say for this particular example, the compressor is replaced. The compressor that used to be here is replaced now by how many components? You got the absorber right here, you got the pump, and you got the generator, and you got a valve. You know, one component that's replaced by 4. Number 2, so what's happening in the absorber? In the absorber, ammonia vapor coming from the evaporator at state number 1 is absorbed by a liquid. Okay, so it gets absorbed by a liquid. And then in the generator right here, heat transfer from a high temperature source drives ammonia vapor out of the solution, right? And everything, you know, kind of resumes in a normal fashion. Now, but even with this problem, there are some issues. Why? There are some issues because, you know, when you're evaporating something like this, you're not really getting just 100% of refrigerant, you know? If you get some water droplets in there, you know, that could cause issues, you know, in this case. So it says ammonia water systems, you see here, yet another variation of it. And remember, my goal here is just for you to understand what this is doing, you know. It's not like we're gonna be analyzing this or anything like that. So you got the absorber, okay? This is as before. The pump is as before, right? And it says ammonia water systems normally employ several modifications to the simple absorption that we just talked about in the previous slide. The 2 common modifications are, first, in this cycle, a heat exchanger. Anytime you see something like this, it means it's a heat exchanger. This is obviously a counterflow heat exchanger. One fluid is moving upward, the other one is moving in the other direction. It allows, okay, what is the use of this? I mean, why is it useful for? Well, it says a heat exchanger is included between the generator here and the absorber, so somewhere in between, that allows the strong water ammonia solution here to enter the generator, entering the generator to be preheated by the weak solution. Because remember what we were doing in here, in the generator. We had the rich solution, right? And then we were putting in a lot of heat to separate the refrigerant vapor from the liquid, right? Now, that stuff is, the vapor is supposed to go to the condenser, right? So that the heat comes out, but then the other weak solution is returned where? To the absorber. But in what state? It gets returned in here. It's pretty darn hot. It's a lot of exergy there, right? So why do I just need to bring it in here and then have that heat also go out? So why not use that heat for something, right? So you generate a heat exchanger here. Now this pumped stuff that you're pumping from the absorber right? It gets passed through the generator, through this heat exchanger. So what's the benefit, you may ask? Well, the benefit is that you're not gonna be putting in as much Q in here to separate the two. At least you are using a portion of that heat, you know, from something that you would otherwise just be throwing out. I mean, kind of view this, it's all about savings, you know, and efficiency. So this heat that would go here would just go out, period. So why not pass it through something? Now I'm heating up this guy because eventually I need to heat it up anyways, right? So why not use some of it to do that? So that's the first modification is right there, thereby reducing the heat transfer to the generator. So the only goal of this is to actually reduce this guy. Number two, the other modification is happening somewhere here. Because what comes out of the generator is supposed to go directly to the condenser, right? This is supposed to be the refrigeration vapor, right? So the other modification is the rectifier, which is placed between the generator and the condenser. The function of the rectifier is to remove any traces of water from the refrigerant before it enters the condenser, because if they cool off, obviously, what cools off, what solidifies first, or what becomes ice first? It's the water. Right, the water is going to freeze first. So the function of the rectifier then is to remove any traces of water from the refrigerant before it enters the condenser. This eliminates the possibility of ice formation in the expansion valve, because you don't want, otherwise, you know, you just be moving on and then you have ice buildup in there, you know, and of course your stuff just gets messed up. This eliminates the possibility of ice formation in the expansion valve and the evaporator. Again, going from the physical academic vapor refrigeration cycle, which has just those 4 components, but in real life, obviously, people make all these modifications of multi-stage expansion, multi-stage compression, plus anytime you add a modification, there's another problem that you have to worry about. That means you have to reroute this, you have to reroute that. And obviously, in this particular case, we have to figure out the state here, the state there, the state there, state here, state there. You know, then it becomes kind of a little bit of an issue, okay? But the book only mentions these, and that's it, you know? We don't even have any example problem or anything like that, but I think it is worth to at least see it as a modification of the regular refrigeration cycle. Now, let's move on to the next section. The next section talks about heat pump. Heat pump is no different than a refrigeration cycle. You're still operating between a cold space, a hot space. The only difference between a refrigerator and a heat pump is the goal, okay? In fact, it only gets reflected to one quantity, which is what? Between a refrigerator and a heat pump. What's the only thing that gets changed?
Direction of the cube.
Well, of course, the direction of the cube.
Heating in space,
Efficiency.
cooling in space.
Not the efficiency, the coefficient of
Coefficient
performance.
of performance.
That's the only thing that changed. This one, first of all, this one is called beta. This one is called gamma, right? And the denominator is the same, right? Except that here it's Q, C, right? And this one is QH. That otherwise, everything else is exactly the same, okay? So keep that in mind. So the objective of heat pump is to maintain a temperature within a dwelling or other building above the temperature of the surrounding, or to provide a heat transfer for certain industrial processes. Again, the same thing with heat pumps. They may be same thing, same features as refrigeration systems, so no need to repeat everything else. They can be of the vapor compression, or they can be of the absorption type. because it is the same cycle after all. Vapor compression heat pumps are well suited for space heating applications and are not commonly used for this purpose. Absorption heat pumps have been developed for industrial applications. You know, all that stuff that we've been talking about is really for where you have rectifiers and heat exchangers. That's for really, really heavy duty industrial applications. Again, when you look at this, repeating kind of that same idea that we talked about before for a vapor power system. Remember what we talked about before. We can regard this cycle as a heat pump, right? You're still going from 1 to 2 for this and that, and obviously you remember what we said about the turbine. It does not really exist. This is a Carnot, which has 2 isentropic and 2 isothermal processes. And the coefficient of performance, we use the letter gamma for it, which is really TH, because this is for Carnot. It's going to be obviously TH divided by TH minus TC. Now, you're probably all familiar with this thing in here. We've got the heat pumps that are in typical houses. You have the outside unit, the inside unit, right? As illustrated below, a vapor compression heat pump for space heating has the same component as the vapor compression refrigeration system, right? You still got the compressor, right? And you usually find these, the compressor and the evaporator on the outside unit, kind of in the same spot. And then the expansion valve, and then the condenser on the inside. So Q in comes in from the surrounding. So even on cold, wintry days, you're still extracting heat from the cold air that is outside and dumping everything else inside, right? And Q in comes from the surrounding, and Q out is directed to the dwelling as the desired effect. Again, desired effect, the desired output divided by input. And for the heat pump, it's obviously gamma, which is the Q out now as opposed to Q in for being the refrigeration, right? You don't care about how much you're cooling the surrounding air here. You're cooling, it's how much heat you're dumping into your space that you want to heat. So that becomes Q out divided by WC, which is H2 minus H3 divided by H2 minus H1. So other than that, I think there isn't really much else that can be talked about, except that, you know, all the heat pumps we have at home these days, right? You can operate them as heat pump, and you can also use them to cool your space, right? So the only way you're doing is really reversing the circulation. The condenser really becomes the evaporator becomes the condenser in a sense. So this is in the most common type of vapor compression heat pump for space heating. The evaporator communicates thermally with the outside air. You know, that outside unit that you have in the house is typically the evaporator, right? But then such air source heat pumps can also be used to provide cooling in the summer, right? With the use of a reversing valve, okay? Here the solid lines show the flow path for the refrigerant in the heating mode. You know, there you go. And, you know, going this way, you know, it's kind of a clockwise direction, if you will. In the cooling mode, the outside heat exchanger now becomes the condenser, and the inside becomes the evaporator. So you're just reversing the flow, and now the inside. Now you're extracting heat from the inside and dumping it to the outside, thereby cooling the inside and heating up the outside. So, to end this about heat pumps, we really didn't learn anything different. All we are saying is the typical refrigeration cycle is exactly identical to the heat pump one. The only difference, that you need to remember is the coefficient of performance, okay? Okay, now, the book has a I have here an example of an actual vapor compression heat pump cycle, but it's kind of refrigerant 134, working fluid and electric power heat source, air source heat pump that maintains the inside temperature of a building at 22 degrees for a week when the average outside temperature is 5 degrees, which is kind of what a heat pump does, right? Saturated vapor enters the compressor at -8, exits at 50, and then saturated liquid exits the condenser at 10 bar. The refrigeration mass flow rate is given, and I don't even know why this power is in here. What is the compressor power? What is the isentropic efficiency? What is the heat transfer rate provided to the building? Coefficient of performance, and then total electricity, and so forth. So when I look at this, again, this is the type of cycle that you have. You probably can see that this is identical to the stuff you go 1 to 2S, come back to 3, and then 4, and then 1, right? So, except that when you have 2, obviously, that means there is an isentropic efficiency associated with the compressor. But again, the 4 different components, 1, 2, 3, 4, and the goal here now is more this than this. So it's really the Q out divided by WC rather than anything else. Now the way you analyze this problem is identical to the refrigeration cycle, so we're not even gonna look at that. Once you get those 4 H values, everything else becomes a quick issue.
Is this example in the book?
Uh,
I'm not even,
It's not in the book?
I don't know, maybe I'm just not seeing it.
Well, it's not in my book either. I must have gotten it from somewhere. It's not in this book, isn't it? It's probably from a newer edition, maybe, of the book. Okay. But I think you got all the things from there. So again, it's really no different. Each, feel free to go back and figure it out for you. For each state, it's 4 states that you need to go through. You know what the temperature is, you know what the pressure is, you can find what H is, what H is, what H is, right? And you probably notice that H3 is equal to H4, as indicated before, and this is the HF associated with that state, and so forth. This one is HF associated with that state. This one is probably the only one that you have to worry about. Now, section 7 is really the last section. We may not be able to, maybe we'll be able to finish this. Gas refrigeration systems is the last section in this chapter. Now we've looked at vapor, refrigeration cycle. We looked at absorption, right? Absorption, we just looked at it qualitatively, not quantitatively. In other words, we did not have a particular cycle that we had to worry about. But this one, on the other hand, will have it's another refrigeration cycle that involves a fluid or a refrigerant that stays just as a gas, okay? So all refrigeration systems considered thus far involve phase change Now we can look at one in which the working fluid remains a gas throughout. That means we don't have to go superheated or saturated or this or that. Now, obviously it's gas because it remains as a gas throughout. They have a number of important applications. They are used to achieve very low temperatures for the liquefaction of air and other gases, and for other specialized applications such as aircraft cabin cooling. Now, the Brighton refrigeration cycle illustrates an important type of the gas refrigeration system, and this is the one that the book just shows you, you know, as an example. And this is what it means. Obviously, it has, remember the Brighton cycle has two constant pressure cycles, two constant pressure processes interspersed with two isentropic processes. So isentropic constant pressure, isentropic constant pressure. And remember the isentropic ones are occurring, constant pressure ones are occurring through the heat exchangers, right? And the isentropic ones through the other components where you have no heat transfer or stuff. But compressor and turbine, in fact, this is where what's happening through here, is it the isentropic or constant pressure? Isentropic through here, through there, constant pressure through there and there, right? So again, remember, case number one is always the entrance to the compressor, okay? So what do you do with your working fluid? You're compressing it. In the process of going from 1 to 2, you're increasing the pressure, you're increasing the temperature, right? So then you pass it through a heat exchanger. So this is, and then you lose, we don't call it a condenser. Why? Why don't we call it a condenser? Because we don't talk about vapor phase change, right? It remains a gas. So all you are doing there is cooling, right? And when you talk about cooling, you think of heat exchanger rather than anything else. Whereas when we talk about vapor power cycles, we're pretty specific. You know, we say it's a condense. So we have a heat exchanger, and we see always after you compress, after you heat, you don't add more heat. You remove the heat, right? And then after that, you pass it through a, this is high pressure, right? And then you pass it through, the temperature between 2 and 3 goes down, right? Because you have some heat transfer to the warm region. And then between 3 and 4, now you are expanding to the lower pressure because you're still at high pressure here. You need to go back. Anytime you need to go back when you have fluid like that, air, you expand through a turbine, one stage, come back to the lower, and you do it isentropically, you come back to state 4S, and then what happens? Now you have low pressure, low temperature, right? As it passes again through this heat exchanger, it absorbs heat from the cold region, okay? So you have one space in which you are removing heat or losing heat, in the other one you have, you're adding, you're extracting heat. Now, looking at this Brighton refrigeration cycle, which is the reverse of the closed power one, remember for the other one we had what? We had the turbine that was producing what, and remember, both the shaft is connecting to both the turbine and the compressor. So looking at this, what is the work done by the compressor? Again, it's all a function of the H's, right? H2 is going to be higher than H1, so it's H2 minus H1. What is the work of the turbine, right? Should be H3 minus H4. What is Q in here? It should be H1 minus H4, right? And what is Q out for that matter? H2 minus H3, and so forth, right? So, because this is a refrigeration cycle, and the goal is to keep this guy as cool. Now, what is the coefficient of performance? Is it a beta or a gamma? It's obviously a beta, because beta goes with refrigerators and gamma with heat pumps. So it's going to be the Q in divided by the net work. It's not divided by WC or that. Here you have two components that are doing the stuff, so there is a net amount of work that you are applying, which is the work of the cycle, which is WC minus W1, and therefore it's going to be H1 minus H4 over H2 minus H1 minus H3 minus H4. So again, nothing out of the ordinary for this one, in my opinion. It's really straightforward, right? And to analyze something like this, all you need to really establish is 4 values of the enthalpy, okay? And this is yet, in this chapter, it's obviously the vapor power refrigeration cycle plus the Brighton cycle on this one that you need to be familiar with. So in terms of cycles, this is kind of the last one that we're going to be talking about. Now we're going to, starting next week, we'll be delving into something totally different for the remainder of the class. So quickly here, one example, and I think that should hopefully, how do you analyze something like this? In this case, you are given air as the working fluid, so you know which table you're probably going to be using, right?
22.
22, this is your friend, right? So air enters the compressor, okay, right here. As an ideal Brighton cycle refrigeration at 1 atmosphere and 480. Usually the inside, the first state is always given. So pressure temperatures are given, you're done. You know, remember for these types of things, to find H, what you need to know? What do you need to know? Temp, exactly. So, and then the compressor pressure ratio is 3, and volumetric flow rate is given. Remember, anytime the volumetric flow rate is given, it's AV. Remember, we've seen even this in fluids, it's like Q or AV. If the compressor pressure is 3, and the turbine inlet temperature is 540, what is the net power input, what is the refrigeration capacity, and what is the coefficient of performance? Now, irrespective of what the questions are, I know I need to define this, so I draw my physical system in the cell, and then I draw my TS diagram, because that's what the Brighton cycle is all about. Now, clearly, the problem of interest in here, the table of interest would be table, because these are English units, I think, right? Ranking and all that kind of stuff, right? So it should be table 22E, okay? So what is state number 1? The temperature is 480 degrees, I believe, right? You see the value? H1, yeah, that's what I was looking for. I can see it directly here on page 903 at 5, what is the temperature again? 480. 480. I can see 114.69. Okay, which is exactly what you have here. And obviously, because it is the start of an isentropic process in this case, we don't read the value of S, but we read the value of the PRs. Remember, when you have volumetric stuff, it's the VRs. When you have the pressure ratios, it's the PRs that you need to read, okay? So we need the value of PR1, which is, remember in that, where it says delta S equal to 0 in that table, that means it's only applicable for isentropic processes, right? So for 480, I read the value of PR1 of 0.9182, which is exactly there, 0.9182. So, state number 2 is defined by what then? Right? Well, it's going to be, for state number 2, I can figure out what PR2 is, because PR2 over PR1 is P2 over P1, right? So P2 over P1 is already given. It's the pressure ratio that was given as 3. that means that PR2 will be equal to 2.755. So to figure out then what is the H2, I need to search for something that has a PR2 of 2.755. And if you look at that, what would that be?
11,
it's between, is that 640 and 660, somewhere around there? Because that's 2.51
2.8.
and 2.8, right? And I think I'm somewhere in between, right? What am I? Where the heck am I? Oh, 2.755, yeah. So it's somewhere in between. That means the value of H will be between 153 and 157, right? And 157.9. So if you interpolate correctly, you should get something like 157.1. Okay, that's state number 2. Okay? Then after state number 2, what do you have? State number 3 is given by, what do I know about 3? You know the temperature. Okay, that's sweet. 540. From that table, what is the value of H? That's 129.06. Okay, so you see we got 3 of them already. And then number 4, well, number 3 is that, but between 3 and 4 it's isentropic. That means I need to read the value of PR again, which is 1.386, right? And then I need to compute PR4 based on that, which is PR4 divided by P3 by T3, right? So the pressure ratio when you go from low to high, it's 3. When you go from high to low, it's going to be third. Okay, make sure you notice that, right? And then you get 0.462. Then you come back and search what is the value of 0.462, which happens to be, if my eyes are working, it's between 380 and 400, somewhere around there, or between 90 and 95. Okay, so that's about 94, sounds about right. Okay, done. So once you find these values, then the rest of the stuff becomes pretty straightforward. Except that when you do, you probably have noticed this when you were reviewing your Brighton cycles. If the mass flow rate, for example, is not given to you or something like this, remember this famous equation, AV over V, you know, that's a common one. And sometimes an ideal gas equation may be asked to do. So the net power is really the power of the turbine minus the net power is the power on the compressor minus the work on the turbine, you know, which kind of gives you this. And then mass flow rate is AV over V. AV is given, but V is not given, so you always have to make use of the ideal gas law, okay, in those events. And so we found the work is 1848 BTU per minute. Refrigeration capacity is what's happening between 1 and 4. And then the coefficient of performance happens to be 0.76. So that example, it's another one that you probably need to be aware of. I'm not going to say much about this. You probably guessed what this is. That's the same problem as before, except that now, what do you have? You have an isentropic efficiency of the compressor and an isentropic efficiency of the turbine. Okay? What is the net effect on this is obviously on the coefficient of performance. That's going to drop down when you introduce those and you work out the numbers. You find that the coefficient of performance dropped from that 2 point something, right, to down to about 0.543 when you have inefficiencies in those things. And that concludes chapter 10. So we will have we'll have chapter 11 and chapter 12 that are that we're going to be continuing on. Chapter 11 actually talks about a little bit of differential math in it, but it's a chapter in which we'll talk about the ideal gas laws, and then how are the tables, properties in the tables, you know, because we cannot have an entropy meter, we cannot have an enthalpy meter, internal energy meter, or something like that. The only thing we can measure on a substance is pressure, temperature, volume, maybe mass. You know, how do we get all the other stuff from knowledge of those properties? And then chapter 12 is going to be an interesting one. That's one in which we'll talk about HVAC things a little bit, psychrometric charts. In other words, we're going to talk about what happens when you mix water vapor with dry air at different proportions. Okay? Then you come up with relative humidity issues and dry bulb temperature, wet bulb temperatures, you know, all kind of good stuff.
Is the exam gonna be like a 2 or 3 question one again, or is it gonna be a normal one with like 5 or 6?
Exam 2?
Yeah.
3 questions, 3 problems.
questions again? Okay.
I said.
One auto, one.
I mean, I keep saying it. I'm saying.
Well, I know we keep saying auto, diesel, and
Yeah.
standard, but
Yeah.
I didn't know if we're just gonna have one question.
No. It's just simple problems to those example problems.
Okay.
Just chapter 9.
Just chapter 9.
No exergy.
No exergy anymore.
Are we turning in chapter 10 homework next week or the week after?
If you can do it by next week, that's fine. If you wanna save time and review, then I can wait for the following.
Okay.
Okay.